be Anuraj to introduce the chief guest.
Okay, so let me start.
Now I request to introduce the resource person by Dr. Anuraj sir.
Okay. So very good afternoon to all of you. So I'm happy to introduce our resource person, Professor Sergei Popov from Russia. I think he has completed his PhD in astrophysics in the year 1998, population synthesis of X-ray source after the burst of star formation and the evolution of isolated Newton stars. So under the supervision of Professor Lipunov. Okay, so he has right now he is working as full-time researcher in the Sternberg Astronomical Institute and Higher School of Economics, Department of Physics, professor. So various positions he is held in the different universities. Okay, so he visited so many abroad countries like Italy, German, Poland, Spanish, and Germany. So if you see the publication, it shows the reputation. So he has more than 160 publications in reputed scientific journals, and so also he is a member of Expert Council of Russian National Higher Attestation Committee and member of Scientific Council and Sternberg Astronomical Institute. So his profile, if you read the profile, so 1 hour is not enough to read complete profile. I have shortened the profile. So such kind of resource person we have for the today's session. So I request all the participants to listen carefully and patiently and utilize the session effectively. So welcome you all for this lecture. So with this few words, so I give it the session to the Professor Popov. So Popov, you can deliver the lecture, I think.
Okay, thank you.
Thank you, sir.
So I'll speak about astrophysics. So I suspect that for most of you, it would be just a kind of educational talk. But I'm going to speak about a very hot subject, and quite often in mass media you can hear, you can see, you can read news about these fast radio bursts. It's a puzzle. These transients are still not completely understood, and I'll try to show you many slides with all phenomenology and with many theoretical approaches developed in this field. And so finally I will come to intermediate, say, conclusions, because the puzzle is still not solved. Okay, so let me start with an introductory slide, because you can ask a very obvious question: why the puzzle of these fast radio bursts is so new? Why it is very difficult to study transients in radio astrophysics? The problem is in technology. Typically, when people perform radio observations, they are dealing with very narrow field instruments. It's very difficult to make a kind of all-sky survey. And that is why mostly in radio astronomy, people study persistent sources, which are not drastically variable, or they can be variable, but they also have persistent emission, so it is quite easy to discover such sources, and then you can study them in details and finally discover the variability. On the plot, you see a diagram, say. On the vertical axis, the luminosity is presented, and on the horizontal axis, roughly duration of the transient event. And there are very different transients. Mostly, of course, sources are variable. There are stars, there are active galactic nuclei, so supermassive black holes in centers of galaxies. Of course, there are radio pulsars. Here they are. And here on the left and on the top, you see fast radio bursts. So obviously, they are significantly shifted from all other types of radio transients. They are very short, they have millisecond duration, and they are very intense. So their intrinsic luminosity is very high. It's like 1 billion luminosities of the sun, purely in radio wavelengths. And so from the very beginning, I would say, it was clear that we're dealing with something new, something very interesting and atypical. Okay, let me present a brief history. The first paper was published on the subject in 2007 by Dan Lorimer. Then there was the second event only 5 years later, and the main burst of activity started in 2013 after the paper by Thornton and his co-authors. In 2016, the first repeating source was discovered, which was a major discovery because for the very first time it allowed to localize the source, to find the host galaxy of the source, and so to start studying it in details. Okay, about the first burst. The first paper was published, as I said, in 2007. From the very beginning, it was clear that we are dealing with something very interesting. And the paper was published in Science, so in one of 2 main scientific journals in the world. The burst came out from nowhere, so it was, say, kind of blank part of the sky, no nearby galaxies, no interesting sources, just there was a very strong burst. And what you see on the plot on the left, this line, you know that that electromagnetic waves propagate with what we call velocity of light in vacuum. Then the velocity is unique for all wavelengths. But if an electromagnetic wave propagates in plasma, then high frequency signal propagates with larger velocity and low frequency signals with lower velocities. So there is delay. And on the vertical axis here you see frequency, and on the horizontal axis time, which represents delay. And you clearly see that the signal is significantly delayed. So it's milliseconds, and it's really a very significant effect. How it can be? It means that on the line of sight, on the trajectory of this electromagnetic wave, there were lots of electrons in plasma. And we can clearly see that all plasma in our galaxy in this direction is not enough. So the source must be A, extragalactic, B, very, very far away source. So the distance might be very large in order to obtain this large delay in arrival. So it was possible to estimate the distance, and it came out that the distance is several billion light years, so about 1 gigaparsec. If you calculate then the luminosity of the source, it appears to be very large, 10 to 43 ergs per second. In astrophysics, we usually use CGS units, not SI. And 10 to 43 ergs per second, it's several billions of the solar luminosity. And here it's only in radio wave. A few words about the dispersion measure. Dispersion measure shows you how significantly the signal is delayed. So how many electrons are on the line of sight. And the time delay is inversely proportional to the square of the frequency. And this coefficient here is this dispersion measure. So it's integral along the trajectory of the number density of electrons. So you obtain this number, and it tells you how many electrons are on the line of sight, and then you can calculate distance. We can do it for our galaxy. I will not stop on it in details. Our galaxy has a spiral structure, and then electron density is higher in these spiral arms, but we can all take it into account, and for this source it was clear that galaxy is not enough. So you can make a t-shirt with a sign with a writing galaxy is not enough, and then this nice plot of the first fast radio burst. Okay, maybe I'll skip it. So the first event, as I said, was found occasionally. It was serendipitous discovery. People were observing this region near the Magellanic Cloud. These funny circles represent the diagram of sensitivity of the radio telescoping parts in Australia. And the source was discovered as a bright source just in one beam of this diagram. And the field here is not very small. I'll show you later. It's about the size of the moon on the sky. But there is nothing interesting inside. And the source was very bright. In radio astronomy, they use funny units called Jansky. And 30-40 Jansky is a lot. Typically, radio sources have luminosities like millijansky, and this was like several tens of thousands brighter. History seemed to be repeating. Maybe you know that in late 60s, with the system of American satellites Vela, which were spy satellites to look for nuclear tests in then in USSR and China, they discovered gamma ray bursts, which actually came from nowhere, from the universe somewhere. And it was a puzzle for more than 20 years. Only in the late 90s, people understood what are these gamma ray bursts. They came out to be cosmological events with huge energy release. And now it looks like we have the same. There are mysterious radio bursts on the other side of the range of electromagnetic waves. And they also come from nearly blank field. Localization is very poor. It's very difficult to understand what they are. So people made many hypotheses about it, and I'll talk about it during my talk. The second event appeared 5 years later, and it was not so spectacular. Also, it was in the galactic plane, in the plane of the Milky Way. And so there were kind of discussions if they are really cosmological or not. Also, people started to find funny signals in radio telescopes, which got a very funny name, peritons. So you see, it's a deer with wings. And it's from Wikipedia. You can go and check yourself what are peritons. They look to be artificial signals, something coming maybe from Earth magnetosphere, maybe from some technological devices around, but they looked very similar. They were also millisecond. They show kind of dispersion measure, but you see the line is patchy. So it's not a smooth line like in the case of the Lorimer burst. But still, these events were numerous. There were dozens of them discovered. And really, cosmological FRBs, as we know now, were just 2 at that time. So there were doubts if this is really an important problem in astrophysics. But the situation drastically changed in July 2013, when a paper by Thornton appeared, and they presented 4 clear examples of fast radio bursts. And actually, in this paper, they suggested the name fast radio bursts. And from this point, people understood that we're dealing with something really astrophysical. In addition, very soon, these 2 ladies in Australia discovered what are peritons. It's a very funny stuff to read it. And this paper in which they describe it is really interesting. It's a very interesting piece of science. When people are dealing with noise, with fake signals, how they control it. So peritons came from microwave ovens at the observatory. It was a kind of epic fail, because of course you should not use such devices in the observatory. Be very careful with them. But as people never worked with such rapid transients, they didn't care about tiny signals of these microwaves. But it came out that they produce them, and potentially they could be mixed with fast radio bursts. But thanks to these 2 ladies, now we know what are peritons and what are fast radio bursts. Okay, so the problem of fast radio bursts became pure astrophysics at that time, and as we'll see later, people start to suggest theories. But of course, to deal with theories, you need experiments or observations, because you need to reject theories, you need to exclude them. And finally, like Sherlock Holmes told us, when you exclude all impossible variants, the one which is left is real, even if it also seems to be impossible. So people suggested many theories, but you need observations. And what was important that up to May 2014, all fast radio bursts were found in archives. So people offline months or maybe years later reduced data very carefully with new algorithms. It's very difficult to find short non-repeating bursts in radio astronomy. So they carefully reduced the data looking for these bursts. And then, of course, you cannot follow up. It happened 5 years ago, something bumped in the sky, and that's all. In 14, people finally were able to find the burst online immediately, and immediately trigger additional observations in other wavelengths. Because if something is bursting, presumably you can expect signals in optics, in gamma rays, in X-rays, but you have to look quickly, you have to do it rapidly. And people triggered observations in other wavelengths, and they excluded known bright transients like supernovae, like gamma ray bursts, which we already discussed, and several other types of transients. It was very important. So known types of bright catastrophic events with huge energy release were rejected by these observations. So at first, only the radio telescope in Parkes in Australia discovered fast radio bursts. Then other instruments started to take part in this astrophysics. And now we have more than 100 reported bursts. I didn't check, maybe now it's like 118 or something. I checked a few days ago. As you see, many radio telescopes all over the world, in the southern hemisphere, in the northern hemisphere, are observing fast radio bursts. And of course, much more instruments participate in follow-ups. And you can look at the catalog on the special website dedicated to this field of studies. Still, in astronomy, to study sources, we need to localize them very well. So you can look with many different telescopes working in different wavelengths in this particular tiny piece of the sky to see what is happening there. But for single short bursts in radio, it was impossible to localize it precisely. And it's still impossible with, say, one telescope. So Parkes is one. This is the funny picture of the beams of sensitivity of this radio telescope. And as you see, the size of this circle is about the size of the moon, half of a degree on the sky. So it was impossible to localize the source with better than 10 arc-minutes accuracy with Parkes. It's not enough for astronomy. So the first years of studies were, say, dark and obscured because of impossibility to localize the source precisely. The situation changed when the first repeating source of fast radio bursts was discovered. It was done with a very large antenna, with the Arecibo telescope. It's famous because it was used for different programs for searching of extraterrestrial intelligence, for example. The importance here is that it is huge, so it is sensitive to very weak signals, and they made follow-up for one of sources of FRB. So there was one bright burst. They follow up and they found many other events. At first it was 10 events, now it's like 1,000 events, I think, in a few years discovered from this source. It is important because if the source is repeating, you can start a joint program with many telescopes all over the globe, and with a kind of triangulation, you can pinpoint the source on the sky with extreme precision. And it was done thanks to different telescopes working all together in States, in Europe, all over the world. So you see here the list names of telescopes, dates, and you see that there are simultaneous discoveries which allow to localize the source very precisely. So people found the galaxy, and not only, they even found the exact place inside the faraway galaxy where the source is situated. It's really a faraway galaxy. 1 gigaparsec is like 3 billion years, slightly light years, slightly more. And the galaxy is unusual. It's a dwarf galaxy with very high rate of star formation. It means that there are lots of massive stars with short lifetimes. These stars explode like as supernova, produce young neutron stars and black holes. So it became clear that FRBs are linked to young population. Most probably with neutron stars, I'll come to it later. So this is a very precise localization of the source of the fast radio bursts, and it is situated not just in a galaxy with high star formation rate, but exactly in the region of extremely high star formation. So that was very interesting and important. As the source is repeating, it is possible to trigger programs not only with radio telescopes, but with different telescopes. And people started to monitor this source with very sensitive telescopes of different kind. In the first place, with X-ray telescopes, Chandra and XMM, two major observatories in space were used for that, and they found nothing. The same zero result was obtained for gamma rays, this data from Fermi, and not only for the repeating source, but for other sources too. Also, it was, well, different FRBs were monitored with the Indian satellite AstroSat. It's an X-ray satellite. Also, it gave zero identification. And up to now, we don't have any counterparts for extragalactic fast radio bursts. People understood that finding repeating sources is very important, but it's very difficult to do. It was difficult until a special new instrument appeared. It's a telescope called CHIME. You can see it on the photo, and it is situated in Canada. Canada is a kind of good because it's in the northern hemispheres. Before, main instruments were in the southern hemisphere in Australia, like Parkes, Atmos, ASCAP, now Meerkat in South Africa. And CHIME started to operate in 2018, and relatively quickly they found another repeating source. Then the third repeating source was found in Australia with the system of radio telescopes ASCAP. And then CHIME started to present many repeating sources. In the first set, they presented 8 repeating sources. Actually, they are not so very repeating. Some of them produce just 3 bursts. Not so much, but still it is important. We collect data, we improve statistics. And studies of repeating bursts allowed to make another important discovery. This year in January, so all the science I'm telling you is really very new, and the situation is changing very quickly. So this January, people announced the first clear example of periodicity in FRB bursts. Actually, they not work like a clock, say. It's more like I'm going to the university. Okay, now we are working from home because of COVID, but still, it doesn't mean that I appear in the university every day exactly at 9 o'clock in the morning and stay till 6 in the evening, for example. No, but there is some periodicity in my appearance in the university. I appear, say, in a daytime, on working days, and I don't appear at the university deep in the night, for example, early in the morning. I hate that, wake up early. So more or less the same works for FRB for this particular FRB. People found 16 days periodicity. So during this period of activity, you can detect bursts, and you don't detect out of some particular phases of this 16 days period. So till now, we don't know the origin of this periodicity. Most probably it's a binary system. So a neutron star which produces fast radio bursts rotates around a massive star, for example, but other options are also discussed. A neutron star can precess, for example. So it's an interesting subject because you can invent many different hypotheses and play with them. Last set of repeating sources from Chime included 9 sources, and they have a special catalog of their detected on this radio telescope of their repeating bursts. And if you are interested, you can see the list here. Okay. Step by step, people started to localize more and more fast radio bursts. And here the main player is ASCAP. It's Australian pathfinder for the SKA radio telescope system. What is important, because ASCAP is not a single telescope, but a system of telescopes, they work like an interferometer altogether, and they can localize even a single burst very precisely. And that's good, because we have still very few repeating sources and a lot of non-repeating sources. The other important piece of information you get from such observation is the type of galaxy, because some galaxies contain lots of young stars, neutron stars, and so on. Supernova explode very often there, and life is interesting. Some galaxies are old and dull. And in this case, the source was found in a galaxy which is classified as a lenticular galaxy or an early type galaxy. And it has relatively low star formation rate. So it's very interesting to put all these pieces of information all together. The third localization came from another instrument, the DSA-10. It's also a set of antennas, a set of radio telescopes, and they also could and can localize non-repeating bursts. And it's again another type of galaxy. So let me remind you, the first was a dwarf galaxy with very high star formation. The second was galaxy with very low star formation. The third was a massive galaxy with intermediate star formation. So it's, well, sometimes, of course, it's disappointing that they are not alike, but it actually makes life interesting, diverse, and it's much more difficult to fit your model, fit your hypothesis to satisfy all these observational results. The fourth localization was important because here, as it was predicted before, fast radio burst could be used as a probe of intergalactic medium. In astrophysics, we cannot do experiments, so we have only observations, and we need variety of very precise observations to understand properties of different sources. And fast radio bursts are very good in this sense because they're very short bursts. So it's really like a probe. You know, for example, when underground nuclear explosions were allowed, it was good for geosciences because they produced sound waves, seismic waves, which propagates through the Earth, and different seismostations all over the Earth could record the signal, and we learned a lot about the internal structure of our Earth. So people needed some special signals. Still, I agree that nuclear tests is not a very good and safe thing. But in astrophysics, we're dealing with natural phenomena. And in this sense, FRBs are safe and good for us. So they work like such probes, which allow you to understand properties of matter on the trajectory of the electromagnetic wave on the line of sight. And so the source was not only localized, but it was understood that it passed through a halo of a galaxy on the way. And so we can understand properties of matter in the galaxy. And it was just the first step. I'll show you later a very fresh and important result. With another burst, it was possible to probe halos of known nearby galaxies, M33, so-called triangular galaxies, not because it has a shape of triangle, but because it is in the constellation triangle, and M31, which is better known as the Andromeda galaxy. Then there was the fifth localization. Okay, I'll skip it. And recently in May this year appeared a set of papers. Actually, it was not a single paper by ASCAP, in which they presented 4 new localizations. And what is important, they used several localizations, well, all obtained by this team, to probe baryonic density in the universe. So it was, of course, a Nature paper. And they confirmed this known result that about 5% of matter in the universe is in the usual form, which is closer to your sight. So normal matter is what you can find in the periodic table, hydrogen and helium mainly. And for the very first time, it was possible really to see, to measure this baryonic density in different directions very precisely. And I think it's the most direct way now to probe the baryonic density in the universe in astronomy. Okay, another thing about fast radio bursts, which is puzzling, which is impressive, but which I didn't mention yet. The funny thing is that they are extremely frequent, extremely. Imagine there are up to 10,000 bursts in the sky in a day. Of course, we observe a tiny amount of this huge number because, as I said, radio telescopes have very narrow field of view. But these events are very frequent in the universe. They're very powerful, but before 2007, we didn't know about them at all. And only 7 years ago, even slightly less than 7 years ago, we started to study this phenomena in details. We obtained some non-negligible statistics and so on, but they happen very often. Nearly every time you breathe, roughly, there is a fast radio burst somewhere in the universe. That's really impressive. But to proceed with understanding of physical mechanism, we need more physical data. And another important result was related to discovery of polarization of fast radio burst emission. And it was done for the very first time in 2014 for this burst, which was the first one identified online immediately. And then people measured several other examples, and now we have like a dozen of fast radio bursts with measured polarization. What does it mean? It means that there is significant magnetic field in the site of emission. And it not very directly, but actually points towards neutron stars. Because later I hope to come to a huge list of hypotheses, and different hypothesis was put forward. But neutron stars from the very beginning was, I would say, a leading approach. Of course, even with neutron stars, you can imagine, you can invent many types of hypotheses, but neutron stars are really the best. Also, we can make a t-shirt, neutron stars are the best. And measurements of polarization relatively clearly points towards neutron stars. Okay, so let me come to the list of hypotheses. Actually, there is a special review about hypotheses about the nature of fast radio bursts. And you can find it, and there'll be a reference to it later on. I here listed just 12 hypotheses. There are much more, and each of them has many variants. So I quickly pass through some of them. Roughly, these hypotheses can be divided in two main classes: neutron stars and exotics. Neutron stars, I told already why. Why exotics? Because, well, imagine that you are a theoretical physicist. So you are studying some funny things which most probably don't exist in nature. It's quite natural. And some years ago, we made a popular science movie with a colleague, and there were several interviews inside. And a prominent Russian young theoretical physicist said a very interesting and important thing, in my opinion. He said, so it's a quotation, in my opinion, theoretical physicists must study things which do not exist in nature, because things that do exist in nature will be discovered in experiments. And we can study, in theory, we can study what could exist in the universe, but for some reason doesn't exist, at least in our universe. End of quote. Okay, so you are a theoretical physicist, you have funny ideas, you published this idea once, and did somehow unpolite to publish it twice, yes, because it's still the same idea. And when you get a tiny chance to say that your idea is probably related to a new experiment or to new observational result, you immediately write a paper. So people working on different exotics in theoretical physics, in theoretical astrophysics, when they got an opportunity to link their favorite idea with fast radio bursts, of course, they immediately grabbed this chance and published a paper. So there were several actually papers that fast radio bursts are produced by cosmic strings. Personally, I think that cosmic strings do not exist in our universe, but they can potentially, and potentially they can produce bursts. When people presented this second fast radio bursts, they noted that it can be related to evaporation of a primordial black hole. I remind you that Martin Rees proposed, and I think also Blandford, proposed already in the 70s that latest stages of black hole evaporation can also produce a radio burst. And actually, it's much easier to detect a radio burst, of course, if you are looking towards it, than, for example, a gamma ray burst. And you can read even in Wikipedia the history of developing the Wi-Fi technology. And you can see there that the major step was made by radio astronomer, by John O'Sullivan. And actually, he came to radio astronomy with the hope to find evaporating black holes. So everything is mixed with everything. Everything is linked with everything. Then many types of hypotheses dealing with neutron stars exploit such an idea. You have to do something with the magnetosphere of a neutron star. You have to shake it to, I don't know, produce some major perturbation in it. And people studied many scenarios how they can do it. For example, a binary system, a neutron star with a magnetosphere and a massive star. The massive star explodes as a supernova, and the shock front hit the magnetosphere of a neutron star, and it potentially can produce a burst. Also, there was a paper of this kind. You can perturbate the magnetosphere of a neutron star with something different, with a gamma ray burst, with the active galactic nuclear activity, and people also studied these variants. Of course, you can perturb one neutron star with another. You can look at coalescences of neutron stars. And of course, it was discussed, and it was quite popular for maybe 2 years, especially when people identified a fast radio burst in an old galaxy with low star formation. I hope you remember that was the second localization. It is important because neutron stars coalesce when they are old enough. So you don't expect that it happens very often young galaxy. They need to live a life before they coalesce with each other. And such an event also potentially can produce radio bursts. You can coalesce not neutron stars, but white dwarfs. You can also have a collapse of a neutron star to a black hole. You can form, after a supernova explosion or after coalescence, for example, a very massive neutron star. They're called supramassive neutron star. For example, Microsoft Office doesn't know this word, and every time I write supramassive neutron star, it tries to suggest me that they are supermassive, not supermassive. No, these are different. Supermassive and supramassive are two different words. So supermassive neutron stars, they might collapse to a black hole, but they are still stable because they are rapidly rotating. When they gradually slow down, finally they collapse, and this, as was put forward in this hypothesis, can produce a fast radio burst. If black hole is not enough, you can use a white hole. And there was a very interesting paper in Nature, you can find it, about white hole evaporation in loop string gravity. It's quite interesting. You can produce much more powerful bursts than in the case of usual black holes. You can use exotic particles, for example, axions. Axions in these are particles not from the standard model, but mostly physicists believe that they are real. There are very important but indirect indications that these particles are very, how to say, welcomed by theoretical physics. So there is so-called Primakov process. Axions can be converted to photons in the magnetic field. So axions are discussed as candidates for the dark matter. This means that they are very abundant in the universe. So this means that they can be very abundant in the universe. And if a cloud of axions pass through magnetosphere of a neutron star, they can all together start to be converted to photons. And so you will see a burst of electromagnetic emission. We don't know the exact value of masses of these particles, and it is possible, as it was speculated, that masses are in the range that allows you to produce a radio emission after conversion. What else you can do with the neutron star? You can transform it to a quark star. So normally quarks are confined in protons and neutrons, but there is a hypothesis that at high density, another state of matter is the ground state, and it's quark matter. Sometimes it's called strange matter because you need the third quark, the strange quark, and it can happen by itself in dense media inside a neutron star. And of course, if it happens, the whole structure of a neutron star is very rapidly changed. And in response to these perturbations, the magnetosphere also rapidly changes, and it can produce a burst. Finally, you can throw something on a neutron star. So something very natural, throw something on a neutron star and produce a burst. And people still discuss, even today in the morning, check the archive. Maybe I have to make a note. I'm sure that you're all familiar with it still. I refer to all publications with their numbers in the archive, so on the site arXiv.org. And this morning, before the lecture, I checked the archive, and again, there was another paper about asteroids falling on neutron stars, producing fast radio bursts. So potentially, it also can work. But the main model now is related to activity of a very particular type of neutron stars, of magnetars. Magnetars are not just neutron stars with high magnetic field. Magnetar means that the luminosity, the activity of this neutron star is determined by the energy stored in the magnetic field. So magnetic field has energy. So the energy density, the magnetic pressure is B squared divided by 8 pi. And magnetic energy can be significant. What is more important is that you can very rapidly release it. because finally we're dealing with currents, and you can very rapidly, with a shortcut, get energy from a current. So as you remember in the first part of Back to the Future, when their nuclear engine was not working, they used a lightning to power the engine. So it's a very good way to obtain very huge energy release in a short time. And immediately in 2007, in DC print, we proposed that fast radial bursts can be related to magnetars. And a few years later, Yuri Lubarsky developed the first model. Now there are many, and again this morning there was another paper with developing this line of calculations. Yuri Lubarsky developed a model in which a huge magnetic hydrodynamic pulse propagating after a flare of a magnetar hits a nebula around the neutron star, and it can produce coherent measure actually radio emission. And this direction of modeling is very popular now, and I would say it's one of two most probable mechanisms explaining the FRB activity. New observations help to exclude some models because people observed if there are FBRs in the direction of recent gamma ray bursts, specific types of supernova, short gamma ray bursts, and so on. I'd skip it. Also, recently, you see the paper, it was appeared in the archive just in May. People analyzed the set of galaxies and concluded that the whole set is better compatible with the magnetar model. This variety of galaxies in which we observe sources of fast radial bursts are better explained by the magnetar model and not by other types of modeling. And from the point of view of rate, magnetars can allow you to have this high rate of events. So on the left plot, you see the luminosity. Actually, that's a minimum luminosity, which goes in some calculations. I have no time to go in details. And on the vertical axis, the distance, the rate in numbers in cubic gigaparsec in a year. And this dark gray shows you the expectations. So actually you have to come to this point on the left from observations, and you see that just soft gamma repeaters, so magnetars, can explain the data. Also, it can be explained by white dwarf mergers, but there are no reliable mechanisms to produce emission now. So I'm coming maybe to the end of the main part. Early ideas included many possibilities to explain fast radial bursts, but gradually people closed all the exotic mechanisms. All catastrophic mechanisms are mostly closed. Why I'm saying mostly? Because it's not for granted that FRBs are a unique population of sources. Maybe there are sources of different kind. And maybe, for example, gamma ray bursts or coalescence of neutron stars contribute a little bit on a level of percents to the whole population. About this percent or 10% level effect, we're not aware at the moment. But catastrophic events cannot explain the whole populations of fast radial bursts. Compact objects plus something also cannot explain the whole population. So the mainstream is related to single neutron stars. Either they are releasing the energy of the magnetic field, as in magnetars, or maybe, but less probable now, I would say, and in a few minutes I'll explain why, the activity of fast radial bursts can be related to rotational energy losses, like in radio pulsars. So we can compare these two approaches, and okay, I have no much time to discuss it. I would say that magnetars win over pulsars, basing on many but indirect arguments. So the magnetar model was developed in several papers. I'll skip it. last August appeared an important paper by Andrei Beloborodov, in which I think he presented a very interesting and detailed model, and this morning actually he and his collaborators presented another paper. Indeed, we observed nebulous around magnetars, so nebulous around these types of neutron stars can be in the game. It doesn't contradict, and it is supported, I would say, by astrophysics, but all the way there was a big question. We know galactic magnetar. Why don't we see fast radio bursts from the galactic magnetar? And galactic magnetars were the last heroes in mass media in relation to fast radio bursts. So the first short radio burst from a known galactic magnetar was detected last year. And it really looks like a fast radio burst, but there are also some differences. And recently appeared a paper in which they studied many this millisecond bursts. In the upper panel you see radio data. The source produces bursts, but they look different from fast radio bursts. So you cannot consider them as smaller analogs of huge transient events of fast radio bursts. Say. But in April, in late April, happened another thing. Another galactic magnetar, that's its name, soft gamma repeater, and this funny number 1935 plus 2154 is represents coordinates in the sky of this source. It's a known burster in X-rays and gamma rays, but in late April, two radio telescopes, in the first place CHIME, discovered a huge and very short radio burst from this source. So a burst consisted of two parts, each of 5 millisecond width and like 30 milliseconds between them. The second telescope, it's not actually a telescope, it's a system with very tiny detectors. The system is called STEAR-2. They also detected this burst, not that nice resolution, but it's a clear detection. They have 4 detectors separated by a huge distance. They're situated in the US. And what is important, simultaneously with this radio burst, people detected an X-ray and gamma ray burst from the source. Actually, not simultaneously, because this dispersion we discussed earlier in the talk. There was few seconds delay. Of course, X-ray emission came to the Earth earlier, faster, because low frequency radio emission propagates with smaller velocity. But you can calculate it, you can take it into account, and then you see that bursts were simultaneous on the side, in the place of emission, in this in the vicinity of this neutron star. So the burst was detected by experiment CONUS on board the satellite Wind. It was detected by the satellite Agile, by X-ray satellite HXMT, and by Integral. So I quickly skip it. And that's the first clear example that a known magnetar simultaneously produced a burst in X-rays, say at high energy. It also takes soft gamma rays, simultaneous burst at high energy and in radio. And in radio, it looks exactly as a fast radio burst. And so many people really concluded that now we are sure that magnetars are sources of fast radio bursts. Maybe it is a little bit premature, because still we are dealing with a very scaled version, because the energetic of this event is a few orders of magnitude smaller than classical fast radio bursts, so we need more observations. Okay, so the current rating of hypothesis is like this. Most probably we're dealing with magnetars. They can be young, they can be old, they can form through different channels. What we do not know exactly is the emission mechanism. we think that magnetars produce fast radio bursts, but we don't know exactly how. Fast radio bursts can be used in theoretical physics. If you are interested, you can just look at the papers, so you can put limits on photon mass, on general relativity. It's quite interesting, maybe. And what is more important is that we get more and more observations, because the problem of fast radio burst is very popular. It's very easy to publish in Nature and Science with it. And many telescopes all over the world, including India, actively takes part in studies of sources of fast radio bursts, of magnetars, and so on. So very nice Indian telescope GMRT in particular participate in it. And people build new telescopes and new facilities, new instruments to study these types of transients. I quickly pass through them. You know that now the largest radio telescope is FAST in China. It has 500 meters in diameter. It's on the left here. They also work in the field of fast radio bursts. We have this funny, cheap, but probably effective STER-2 systems. We hope that X-ray satellites will help to find counterparts. Maybe it will be done with Irazita on board of Russian Spectral G. Maybe it will be done by Astrosat or something else. And I'll stop here on time with my last slide. There are several reviews on fast radio bursts. Still, the field is very rapidly developing. So it's all these reviews, I would say, have very short life cycle. In few years, in 2 years, they become too old. There is a catalog, and there are a lot of sources now there. Well, actually now 9 are localized, but it's a very recent result, so I didn't change it here. In several cases, we can measure details like polarization, rotation measure. And what is more important, people started to discover sources at low frequency. In particular, it's true for repeating sources, because you can invest a lot of time in monitoring these type of events. And for repeating sources, the lowest frequency at which sources are detected is about 300 megahertz. Well, so I'm stopping here. If you have questions, you can write them down in the chat or ask. Actually, for me, I understood it's a little bit easier if you type your questions in the chat, because sometimes sound is not perfect. I don't know why. I hope you hear me clearly. But of course, you're welcomed also to ask your questions just with a voice. Okay, thank you.
Thank you very much, Professor Popov, for your valuable lecture. Now the session is open for audience. If you have any questions, you can ask directly or in the chat box.
By the way, if you are interested, I can send the PDF file of the presentation, so you can send by emails to others or put on the web, whatever you like.
Okay, Professor Popov, thank you very much for your noble lecture. Okay, well, and we are enjoying your session. And the audience are asked to submit your feedback form. And tomorrow we have the third day session of carbon cycle from the Professor Saravanan Ramasamy, USA, and tomorrow at 9:30 a.m. Thank you so much. Okay, Professor. Thank you.